Okay, so we are moving on to chapter 5, and we're going to be talking about probability distributions, which is why we learned how to do probability in chapter 4. And a probability distribution gives the probability for each value of a variable, and we're assuming that these events occurring are by chance. So we're going to talk about whether or not something is unusual in the sense that it might not occur from chance, and that's going to help us as we move forward in statistics. An example of a probability distribution could be if you think about the outcomes from rolling a die. So let me just move to the next slide and then we'll write it there. We have a random variable, and that is going to be represented by x, and that has a single numerical value. So it can't be like favorite color and we'll call it red, blue, green. It has to be a numerical value. And if we thought about rolling a die, one of our possible outcomes for x is the number 1. But so is the number 2 and 3 and 4 and 5 and 6. They're all possible outcomes, and they would be represented by the variable x. And then each outcome is going to be matched with a probability. So the probability that I'd roll a 1 and the probability that I'd roll a 2, and I'm not going to write them all out, but each one has a probability attached to it, and we can write it in a table like this, or we could write it in a graph. So we could have our probability of 1/6 be a height, and we could have all of our outcomes here, 1, 2, 3, 4, 5, 6, and they all have the same height. And we could see that's a uniform distribution. But these together, you match the outcomes and the probabilities together, that's a probability distribution. So we have a couple kinds of random variables. We said they had to be numerical, but they could be discrete or continuous. So we talked about that before. Discrete means there's a finite number of values, or if it's not finite, it's at least countable. So that would be the rolls of a die would be an example of that. The number of people in a movie theater, the number of people in the United States. But a continuous random variable has infinitely many values, and we don't have gaps or interruptions. So it's not like I jump from 1 to 2 people. A continuous random variable is one that could be between 1 and 2. And that means it could be 1.5 or 1.25 or 1.25. And things like weight or height, we would imagine being continuous because there's always a value in between. So if you weigh 10.5 pounds or something weighs 10.5 pounds and something else weighs 11, well, there's something in between 10.75, and there's even something in between 10.5 and 10.75. So that's why we call that continuous. And our probability distributions, what we have to make sure is true before we move forward with anything, is that we know what the random variable is, and we know all the possible outcomes of it and all the probabilities of those outcomes. So we need to have that set up sort of like our die. We know 1 through 6, all the probabilities are 1/6. We want all the probabilities to add to 1 so that we make sure we've considered every possibility, because 1 is certainty. So since 1/6 and 1/6 and 1/6 and 1/6 and 1/6 and 1/6 is 1, I know there's no other possible rolls of my die. And each of those probabilities was between 0 and 1 because they have to be. So if those 3 things are verified, then we can move forward with our probability distribution. And we can look at the distribution, like we said before, in a graph, if that's easier than a table. But it's going to look a lot like the histograms from before, but we're going to have probabilities here instead of frequencies. So we could read for any x value what the probability of that value is. So on here, my probability of 10 would be somewhere less than 0.3. So an example, before we move to our example, there's some formulas we need to know. How do we figure out the mean and the variance and the standard deviation of our probability distribution? Well, the formula for our mean looks a lot like the weighted mean formula that we've used before. What we're going to do is going to take the value for x times its associated probability, and then we're going to add it to the next value of x times its probability, and then add it to the next value of x times its probability, and when we've added them all up, we'll have the mean. So with our die, that would look like 1 times a sixth, and 2 times a sixth, and 3 times a sixth, and 4 times a sixth, and 5 times a sixth, and 6 times a sixth. This is x times the probability of x. And I've got all my x's and all my probabilities, and when I add them all up, that'll be my mean. So that's what this formula does. The variance we've talked about before, it measures the distance from our mean. So the formula is we're going to take all of our x values minus our mean, square that so that it's not negative, and then we're going to multiply on our probability, which is like our weight. And after we've done that, we're going to add up all those answers, and that'll be our variance. This is an alternative shortcut for variance, but we're going to use this formula for the example we're going to do next. And then remember, standard deviation is the square root of the variance. So in another example here, we've got not a uniform distribution. So this is the probability distribution for the number of girls in 2 births. The possibilities are 0 girls, 1 girl, or 2 girls. That's it. The probability of no girls is 0.25 because it's the probability of a boy and a boy. So a half times a half. 2 girls, a girl and a girl, a half times a half. 1 girl is twice that probability because you could have a girl and then a boy, or a boy and then a girl. But with all those probabilities adding up to 1, I know that I've dealt with all the possibilities. So in order to get the mean, I'm going to create this column here that was x times p of x. So my x value, no girls, times the probability that's going to happen, and that's 0. 1 girl times the probability that's going to happen. 2 girls times the probability that's going to happen. Add them all up, and I get my mean. So my mean is 1. On average, you'd have 1 girl. If over and over and over and over again, people had 3 children, on average there would be, 2 children. On average, there'd be 1 girl. So to calculate the variance, I needed to see how far my x value was from that mean of 1, and then multiply on the probability. So this x value minus the mean squared times the probability that happens. That's 0.25. Then the next x value minus the mean times the probability it happens. Well, 1 was the mean, so it's 0 distance away. That's not going to add on to my variance. It's not going to add on to the spread of my data. But 2 is going to, because 2 is different from the mean and the probability. And so when I add up my column, I get my variance, which is 0.25. 0.5, sorry. Adding 0.25 and 0.25 is 0.5. So that's my variance. And the standard deviation is the square root of that. So I worked it out, but on the next slide it has all the values that you need, just like we worked out. And it's the way that you would go about trying to calculate the mean and the variance for a probability distribution when you had all the probabilities you needed. So the answers are, I didn't do the square root of 0.5, but it's 0.707 for the standard deviation. So how do we decide then from a probability distribution whether an outcome that we're looking at is unusual? And we had a range rule of thumb that we used before. We're going to continue to use that. Once we know the mean and the standard deviation, an unusual value will be greater than 2 standard deviations from the mean either way. So 2 standard deviations above or below the mean. If you're outside of those bounds, you'll be considered unusual. So in our example, if we take our mean and add on 2 standard deviations, 2.4, and our mean and take away 2, negative 0.4, those would be boundaries on the unusual values. But if you think about what x is, this really makes no sense. That would mean you had a negative half of a girl. And this doesn't really make sense either because you can't have 2.4 girls. So in this example, because our data was discrete and we didn't have values in between the integers, these don't really mean a lot or make a lot of sense. And finally, we have a rare event rule for inferential statistics that says if under a given assumption, such that a coin is fair or a die is fair, the probability of a particular observed event is extremely small, then we'll conclude that it's probably not correct. So in other words, if you see a probability that's very, very tiny, you could assume that that event is not going to occur. So very, very tiny again. How do you decide that? Well, it has something to do with how far from the mean it is. And if the probability is less than 5%, which is that other boundary we have. So if we're using probabilities to decide, we would want to say that if we have X successes among N trials, so we do something over and over and over and over again, and the number of successes is labeled X, we would say it's unusually high if the probability of having that many successes, or even more, is less than 0.05. Unusually low, then that X value, or having that or lower, is less than 0.05. So usual values are going to have to do with how far away from the mean something is. Unusual values, we're comparing the probability to 0.05. And that's going to come into play a lot more in the next couple sections. So try your homework on 5.2, and I will see you next class.